Today we're going to learn about the 4 basic inverse operations that we need when we're solving equations. So let's begin. To get started, let's consider the following equation. Let's say we've got x plus 3 equals 9. Now I know that a lot of people will just look at this and go, well, if you've got some kind of number, you're adding 3 to it and equals 9, you must have originally started with 6, and you can do that in your head. So why do I need to do anything else? Well, that's all well and good while you've got a problem that's as simple as this that you can do in your head. But not all problems are like that. But it is really crucial to get into the habits of using what's known as inverse operations that I'm going to demonstrate today. So when you come across problems that are more difficult, that you can't do in your head, that you've got the skills and the understanding to be able to solve those problems. So please, while I'm going through this, it's very important to get the understanding and to show the working out of inverse operations. But anyway, let's get to it. Now, when we've got equations like this, we can think of equations very much like a set of scales that I've got in front of me here. And we've got to keep these set of scales equal, in balance. That's what they mean. And we can actually represent this equation on this set of scales. For example, I can represent this x, or this unknown value, as a box of something here. And I'm going to add 3 units of whatever's inside that box of x to that side. And it's going to equal 9 of those individual units on the right hand side to keep it balanced. Alright, I've now got a balanced set of scales and I need to work out how many of these little green dots are in that box of x there. So how do I do that? Well, I could just remove these 3 from here and it would change the weighting of the scales. And to keep it balanced, I'd have to remove the same amount on the right hand side as I did on the left hand side. So let's remove 3 of these. So what am I left with? Well, on the left hand side, I'm left with this x, and on the right hand side, I'm left with 6 of these green dots. So what this scale is actually showing us is x is equal to 6. And to get there, we subtracted 3 from this left-hand side, but to keep it balanced, we also had to subtract 3 to the right-hand side. So to keep an equation balanced, what we've learned is whatever we do to one side, we've got to do to the other side. And that's very important. But now this is where the understanding of inverse operations comes into. An operation is something like addition, subtraction, multiplication, or division, where inverse means opposite. So when we join those 2 words together, what we're talking about is opposite operation. Now in this algebraic statement here, we had x plus 3. And I need to perform the inverse of adding 3 to be able to solve what x equals. So I need to subtract my 3 from the left-hand side, but whatever I do to one side, I must do to the other. So I need to subtract my 3 from the right-hand side. But when I subtracted 3 from the left-hand side, it got rid of that 3 there. So on the left-hand side, I was just left with my x. But on the right-hand side, I was left with 9 subtract 3. And 9 subtract 3 is equal to 6. And this is how we represent what we did algebraically. So therefore, x must be equal to 6 to make this statement true. But the upside to all these sorts of problems is we can actually check to see if we're correct by performing what I'm going to call a check step. What we do in a check step is we take that x value we think it is, we think it's 6, and we replace the x in the original problem, known as substitution, with that 6. So we've got x, or 6, plus 3 equals 9. Now, if we've found the right answer, this should be true. Now 6 plus 3 does equal 9, 9 equals 9, therefore we've found ourselves the correct answer. But let's have a look at what we do when we've got x subtract 3 equal to 9. How might we represent this on our scales? Well, we've still got a box of x here, but instead of adding 3 weights to that side, we're actually going to subtract 3. And to represent that, I've got 3 little balloons here of helium. Now, of course, helium in balloons is going to help lift that scale back up. On the right hand side, we've still got our 9 objects. So I'm going to represent as green dots. Now, how do I find what x equals here? Well, if each one of these balloons lift the scale up as much as one of those green dots would normally push it down, we actually just need to add 3 more of these green dots to this scale to cancel what those balloons are doing. But of course, if we added 3 green dots to that left-hand side and it was balanced when we began, it's not going to be balanced anymore. So we've got to do the same to the right-hand side. Add 3 more of these dots. Now, when we add 3 dots, the effect of these balloons get cancelled out. And on the left-hand side here, we've really only got that box of x. And on the right-hand side, we're left with 12 of those green dots. So what we're saying here is our x value should be equal to 12 to keep our equation balanced. Now you might notice something here. In our original statement, we had x subtract 3, and we need to isolate the x on its own on the left-hand side. And to isolate it, we added 3 from this side. But of course, if we added 3 to one side, it's not balanced. So we've got to add 3 to the other side as well to keep our equation balanced. But what we've done here is the inverse of subtraction. The inverse of subtraction is addition, and this will cancel this off. So on the left-hand side, we're just left with our x. On the right-hand side, we've got 9 plus 3. 9 plus 3 is equal to 12. Therefore, we're saying that our x value should equal 12. But of course, we can always check to make sure we're right. So let's do that. In our check step, we substitute the value for x with 12, which will be 12 subtract 3, and it should equal 9. 12 subtract 3 does equal 9, so what we've got here is a true statement. So x does equal 12. So to summarise, when we've got subtraction from a problem, the inverse of subtraction is addition. Let's have a look at if we've got 5x, or 5 times x is equal to 15. Well, what does 5 times x mean? It means that we've got 5 of these little x boxes on the left-hand side. And then on the right-hand side, we've got 15 of these green dots. Now, if I wanted to know how many green dots are going to be in each one of these x boxes, what I need to do here is to make 5 different piles. For example, let's put our x boxes down in a row like this. So now what I've got is 5 different groups. And now let's divide what I had on the right-hand side by each one of those x boxes. Now, when I make these groups up like this, what it helps show is each one of these x boxes must have the equivalent weight of 3 of these green little dots. Therefore, we can say that x must be equal to 3. But how did we get there? Well, when we group things up like this, we're actually doing what's known as division. And because we're making 5 different groups, we're actually dividing by 5 on each side. And we've now discovered what the inverse of multiplication is. The inverse of multiplication is division. So if we take this problem and divide this side by 5, and I've represented it in fractional form, to keep something balanced, we actually have to divide the other side by 5. Now, of course, 5 divided by 5 is equal to 1, so this side here will cancel out, and we've isolated our x on its own, which is what we need to do. On the right-hand side, we've got 15 divided by 5, which is equal to 3. So therefore, our x value is equal to 3. But you guessed it, we can check to make sure our answer is correct by performing what's known as substitution. So we had 5x equals 15. So that's 5 times our x of 3 is equal to 15. Now 5 times 3 does equal 15. So therefore what we've found is the correct solution, that x must equal 3 for this statement to be true. So to summarise, the inverse operation, or the opposite operation of multiplication, is division. But what if we've got division? What if I've got x divided by 5 equals 3? Now to help visualize this problem, I'm going to show it something different to the scales. I want you to imagine that you've got a group of something, and of that something, you're going to divide it equally amongst 5 different people. And once you did that, every person had 3 of them. So to represent that, I've got person 1 with 3 of these green dots, person 2 with 3 of them, person 3, person 4, and person 5. Now, if I added what each person had all together, we should actually have our starting amount. So when I add all of these together, I should essentially find what my x equals. That means our x must equal 15. But how do I get to that mathematically? Well, let's consider this one person here. This one person had 3 of them. And of course, you knew that every person had the same amount. And you also knew that there were 5 people. So to find out how many total you had, you actually had to multiply it by 5. And this is where the inverse operation comes in. The inverse, or the opposite of division, is multiplication. So to isolate the x on the left-hand side here, we actually had to multiply this side by 5. But whatever you do to one side, you must do to the other to keep it balanced. So we have to multiply the right-hand side by 5. Of course, when you multiply the left-hand side by 5, these cancel, and we've isolated the x on its own, and it's going to equal 3 times 5, which is 15. Therefore, we're proposing that x equals 15. But of course, we can check our answer, so let's do that now by using substitution. We had x divided by 5, but we're saying x is 15. So 15 divided by 5 should equal 3 if we've found the correct solution. 15 divided by 5 does equal 3, therefore we've found ourselves the correct solution. So to summarize, the inverse of division is going to be multiplication. So let's now recap the 4 basic inverse operations. If we start with the addition operation, the inverse of addition is subtraction. If we start with subtraction, the inverse to that is addition. If we start with multiplication, the inverse of that is division. And if we start with division, the inverse of that is multiplication. Okay, so now it's your turn. In front of me, I've got 8 problems here that I would like for you to have a go at solving algebraically by using our inverse operations. In the last 3 problems, I've also included some negative numbers to give you that challenge.